Hello everyone. In this video, we'll continue the theme of depth estimation from the last video. So last time we saw what the depth calculation problem is and how it generalizes some other classical problems like range counting and point location. And we saw that efficient depth calculation can, in general, be a hard problem even if we're allowed to pre-process the input in advance. And in particular, when our query ranges are half spaces, it's impossible to really solve the problem efficiently with just linear space. So that's why we went to the approximate version of this problem instead, where instead of finding the exact depth, we're allowed some error as long as our estimate is within a multiplicative factor of epsilon from the true correct value. And we then saw that this problem actually reduces to the decision version of the problem, where instead of estimating the depth of a range, we're given a threshold z and we have to answer whether the depth is greater than z or less than z. And we're allowed to make mistakes when the depth is within an epsilon factor from z. And after this, we looked at the range emptiness problem, which is an even simpler problem where the goal is to just answer whether the query range is empty or not. That is, whether its depth is 0 or greater than 0. So in this video, what we'll see is this very surprising statement that we concluded last time with, that if we have the ability to answer emptiness queries, then we can actually estimate the depth as well. And this is surprising because emptiness seems like such a much simpler problem compared to actually finding the depth. But it still has enough power to actually do this full depth calculation in itself. So let's see how this is done. So we're going to look into solving the decision version of depth estimation, since as we discussed in the last video, if we can solve this decision problem, then we can use a binary search to solve the estimation problem as well. And just as a quick reminder, here's our goal. So given a query range R and a threshold Z, we want to correctly determine whether the depth of R, which we'll denote as mu R, is greater than the threshold or less than the threshold Z. We're happy if we can do this correctly as long as it's not too close to the threshold. The true depth is not too close to the threshold. So in other words, if the depth is greater than 1 plus epsilon times Z, we want to determine correctly that it's on the greater side. Similarly, if it's less than 1 minus epsilon times z, we want to correctly say that it's on the lower side. And if the depth is within the small epsilon band, then we don't really care what we output. So the goal here is that assuming we have an output that's capable of efficiently answering whether a range is empty or not, can we use this algorithm somehow as a black box to solve this full decision version of depth estimation as well? Okay, so now here's the key idea on how we are going to exploit emptiness to solve this problem. And what we'll do is that we'll use random sampling. So suppose we construct a random sample of the objects from our object space calligraphic S. And let's say we do this by sampling every object with some fixed probability. Okay, so we constructed this random sample. And we can then ask the following question. If we restrict our universe of objects to just this random sample, what is the probability that this range R is empty? So we've made a random sample and then we're asking, what is the probability that our range has intersects with no objects in this random sample? And here is the key observation that we can make. The probability that the range is empty depends on its depth. So let's look at a couple of cases. So suppose the range has a very small depth to begin with. That is, it contains or intersects with very few objects. Then the probability that the range is empty in the random sample is going to be quite high, since we only started with a small number of objects inside the range to begin with. It can be quite likely that none of these objects get picked up in a random sample, and so the range could end up being empty. But on the flip side, suppose if the depth of the range is high, then for the range to be empty in our random sample universe, we would have to pick none of these objects that intersect with the range in our random sample. And because there are a lot of the elements in this its depth is large, since there are a lot of these elements that intersects with it, it's quite unlikely that we're going to pick none of them. So essentially, there's this sort of inverse dependence between the depth and the probability that the query range is empty in this random sample. And this is going to be the key idea that we're going to exploit to solve the depth estimation problem. So let's make this a little bit more formal and quantitative. So as we discussed, we are generating a random sample of the objects, and we'll call this random subset B. Okay? And we'll generate this random subset by sampling each and every object independently to be included in the sample with some fixed probability. Now the choice of probability in itself is not too important, but for concreteness, we'll set the sampling probability to be equal to 1 by z. Well, remember, again, z is the threshold that we want to answer this query for, whether the depth is greater than z or less than z. And this specific choice of probability is not really too important. We're just setting it to 1 by z to make some of the later calculations cleaner. That's it. So, okay, now we'll denote the probability that our range is empty in the sample B as P empty. Okay, so that is P empty is the probability that the range R intersects with no objects in our random sample B. So what exactly is this, the value of this P empty? And we can actually calculate this explicitly. It's not too hard. So our range R, by definition of its depth, intersects with mu R objects, where mu R is its depth. And that's again just what the definition of what depth is. And our object is going to be empty in this random sample. Our range is going to be empty in this random sample only if we pick none of these mu R objects into our random sample. So what's the probability of this happening? So well, each object is being added to our random sample with probability 1 by z. So the probability that an object is not picked in our random sample is 1 minus 1 by z, which is what we have here as a base. And there are mu R objects in total that we're interested in. The probability that none of them are added to the sample by independence of each of these objects being included in the sample is 1 minus 1 by z raised to the power of mu R, since again we are making this choice independently for each object. And so finally the probability that the range is empty is basically just this P empty, and that is this 1 minus 1 by z raised to the power of the depth mu R. So just as a sanity check to understand whether this expression makes sense, what we said earlier is that as the depth increases, we expect that the probability of that this range is empty should go down. And if we look at this expression, that is indeed what happens. So 1 minus 1 by z is a quantity that's less than 1. And when we raise this to the power mu R, as mu R increases, this entire quantity is going to reduce in value. And vice versa, if mu R reduces, P empty is going to, the emptiness probability is going to increase. So essentially what we have here is a functional relationship that relates the probability that a range is empty and its depth. So how do we actually go about using this idea to evaluate the depth? So the key idea we're going to use is the following. So this threshold z is something that we have fixed upfront, and it's a known quantity to us. So from this expression, the probability that the range is empty depends only on the depth of the range, and it's a one-to-one relationship between the two. So in fact, what this means is that suppose if we can somehow find out this left-hand side, the probability P empty, then we can use that to figure out the depth as well. How? Just by inverting this relationship. So you can take logs on both sides and you divide it by 1, log of 1 minus 1 by z, and then you can solve for your mu1. And so you can get an expression for mu1 in terms of your emptiness probability. So basically, if we can find our probability that this range is empty, then we can find the depth of the range as well. And this is where these emptiness queries come in handy. The way we can actually, what we can do is, if we have an algorithm to check whether the range is empty or not, what we can do is we can use that algorithm to estimate the probability that the range is empty over a random sample of objects. So if we can get an estimate of this P empty, we can convert that into an estimate of this depth in itself. So essentially, that's going to be our game plan. We're going to estimate P empty, and then using this functional relationship, use that to estimate the depth. So let's just flesh out the details. How do we actually estimate the probability that our range is empty? For that, we can just use our good old friend from probability, the law of large numbers. So instead of generating one single random sample over our objects, we'll generate m independent random samples of our objects instead, where m is some sufficiently large number. So each of these random samples is in itself a subset of our objects, and we'll call these B1, B2, B3 all the way up to Bm. And the way we generate each of these BIs is by sampling every object with a probability 1 by z, the same way we did it earlier. So if there are n objects in total, each BI in expectation is going to have a size n by z. Since we have n objects, we're sampling them with probability 1 by z. And if we have m such samples, and what we have here is m such samples, independent samples, each of which are of size roughly n by z. So now that we have these random samples, we'll take our query range R, and we'll check whether R is empty in each of these samples. And we'll count how many of these samples our range R is empty in. So if we can count how many samples our range R is empty in, and we compute the fraction, so that is the number of samples in which R is empty divided by m, that quantity by the law of large numbers is going to be very close to the probability that that range is empty, P empty. So this way we can get a really good estimate of the probability that R is empty by doing this kind of repeat, by making multiple samples and checking for emptiness in each sample. And then finally, in turn, we can, once we have an estimate of the P empty, we can use that to check whether the depth is larger or smaller than Z, which is what our original problem is. So we've now assembled all of our moving parts, and now it's just a matter of putting them together to solve this depth estimation problem. So we'll describe this algorithm based on exactly the ideas we just talked about. And this algorithm is by Boris Aronov and Sariel Harpalet from their 2008 SODA paper. So here what we'll do is we'll describe an algorithm and the associated data structure to solve the decision problem. And as we saw, once we solve the decision problem, we can solve the estimation problem as well. And so this algorithm that we're going to be defining is going to use an algorithm and data structure for emptiness as a subroutine. So what we're going to describe essentially is a reduction from the depth estimation problem to the emptiness problem. So basically, for any kind of instance where we can solve this emptiness efficiently, we can use this algorithm as a generic method to also solve the depth estimation problem. So for example, as we mentioned in the last video, for half planes, there is actually an algorithm for solving emptiness, and we can use that algorithm as a subroutine and use this procedure to solve depth estimation as well. Okay, so what's our setup here? So the setup is again the same as we're going to talk about the decision version of depth estimation as always. So this upfront, we're given as input our set of objects calibrated with S. We're given our depth threshold Z that we want to decide whether the true depth is greater than or lower than. And then we're given a multiplicative error tolerance epsilon. So the first thing to do is to pre-process this input into some data structure that we're going to use later to answer queries efficiently. And here's how we do that. So as we saw, the idea was to generate m independent random samples from our object set and use those to use those along with emptiness to solve our estimation problem. And the value we'll set m equal to is this, some c times log n by epsilon squared. So this is basically order of log n divided by epsilon squared. So essentially for a fixed epsilon, the sample size that we're using only grows logarithmically with n. We'll show later when we analyze this algorithm that this setting m to be this large is good enough for us. And because this is logarithmic growth, this helps to cut down on the amount of space that we need for this data structure. So after we set our value of m, what we'll do is we'll generate m independent samples as we talked about, and every sample is generated by picking each object of from our space calligraphic S with probability 1 by z. And so essentially we have these m independent samples. And finally, we'll construct whatever data structure our emptiness algorithm needs on these random samples. So essentially, yeah, this is basically the black box data structure that's used by our emptiness algorithm. And essentially what we're doing by this construction is that each of these emptiness data structures is only going to see a fraction of all our objects. It's only going to be fed in this sample instead of our whole universe object. And it only each of these emptiness, so it's like we have these m emptiness subroutines running in parallel, and they all have their own data structure, and each of them is going to be focused on only this small sample, the small sketch of our entire set of objects. And now that we've constructed our data structure, we'll now see how we can use this to answer queries. And again, our goal is to find out whether the range R has depth greater than Z or depth less than Z. And the way we'll do this is by first running our emptiness queries for this range R on each of the m different samples. And we'll do this using whatever our black box emptiness algorithm, whatever efficient algorithm we have, and we've already pre-constructed the necessary data structures that it needs. And so we can use that to efficiently run these m different emptiness queries. Now, after we run these m emptiness queries, we can use this to estimate the probability that the range is empty by basically counting how many of these samples the range is empty in divided by m. And now, finally, we need to use this. Now we have this estimate of PMT, and we need to use that to decide whether the depth is greater than Z or less than Z. And to do this, if we just go back a little bit, so yeah, we have this relationship between PMT and Z. So we have PMT, or at least we have an estimate of PMT, and the question we want to answer is our mu r greater than Z or is mu r less than Z? Now, if mu r is greater than Z, since PMT is monotonically decreasing as depth increases, so if mu r is greater than Z, then PMT has to be less than 1 minus 1 by Z to the power of Z. And you get that by just plugging mu r equals Z in this expression. And conversely, if the depth is less than Z, then PMT has to be greater than 1 minus 1 by Z raised to the power of Z. And you can use this simple observation to answer the decision problem. So coming back here. So yeah, and this is exactly what we do. We check if our estimated emptiness probability is less than 1 minus 1 by Z to the power of Z. And if yes, then we'll output that our depth is greater than Z. And in the other case, we'll output saying that our depth is less than or equal to Z. So yeah, that's the entirety of the algorithm. It's quite simple. So the last thing we need to do is to justify this choice of m that we use, order log n by epsilon squared. And we have to argue that this size of m is large enough to ensure that this algorithm works, at least with a high probability. And then finally, we look at the query time and space complexity and see how well this algorithm fares. So okay, now let's look at why this algorithm is correct. So what we'll do is we'll show this following lemma, that this algorithm with high probability is going to output the correct decision. So that is whenever the depth is greater than z or less than z, as long as the true depth doesn't lie within this small epsilon band around z, our algorithm outputs the correct decision every time. And this is good enough for us because the way we defined our decision problem to begin with, we're okay with allowing for error when the depth is close to our threshold. So how do we show this? So we'll come to the proof, and we can break this analysis down into two parts. So we can look at one case where the true depth is in the lower regime, that is less than 1 minus epsilon times z. And we can look at another case where the true depth is greater than 1 plus epsilon times z. And essentially we're going to only look at one of these two cases. We'll look at this lower regime where the depth is less than 1 minus epsilon times z. And we'll show that our algorithm in this case is going to output correctly with high probability. The other cases, the analysis is very similar, so I'll skip that for this. So the first thing to observe is that if the true depth is less than 1 minus epsilon times z, then we can say something about the emptiness probability. So remember, the emptiness probability is 1 minus 1 by z to the power of the depth. So if the depth is less than 1 minus epsilon times z, then the emptiness probability is greater than 1 minus 1 by z to the power of this 1 minus epsilon z. So essentially this, if you look at this P empty, it's actually greater than 1 minus 1 by z to the power z. But there's also an additional gap over here. There's this 1 minus epsilon times z gap in the exponent as well on top of that. So essentially the idea here is that the algorithm makes its decision based on which side of the threshold the depth lies in by estimating the emptiness probability and comparing it to 1 minus 1 by z to the power of z. And because we have this 1 minus epsilon times z in the exponent instead, and we have this gap, so really the algorithm only makes a mistake if our emptiness probability is sufficiently far away from the true value, if our estimate is sufficiently far away from the true value, because it has to jump over this gap. And we can be a bit quantitative about this. So the algorithm only makes a mistake when the estimated emptiness probability is below 1 minus 1 by z to the power of z. But whereas the true emptiness probability, as we said, is guaranteed to be above a slightly larger number. And the gap between these two quantities is not too hard to compute. So if you look at the ratio between this threshold and this threshold, you can easily see that comes out to be something like 1 minus 1 by z to the power of epsilon z, which is something like e to the power of epsilon. And e to the power of epsilon roughly behaves as like 1 plus order epsilon using our Taylor series. So essentially this our algorithm only makes a mistake if the estimated emptiness probability is basically less than 1 plus epsilon times our true emptiness probability. So essentially we're only making a mistake if our estimate is at least this 1 plus order epsilon times far away from the true emptiness probability. But the expected value of our estimator, the expected value of this estimator p hat empty, is exactly equal to p empty. So in other words, what we are saying here essentially is that we only make a mistake when our estimate is more than a 1 plus order epsilon factor away from its mean. And we can bound the probability that this mistake is made using the Chernoff bound. So I just written down the standard Chernoff bound here. The probability that the estimate is more than an order of epsilon multiplicative factor away from the true value is at most e to the power minus some constant times m, which is the number of samples we use to make the estimate, times epsilon squared times the true value of the emptiness probability. And this is just what I've written here is just a Chernoff bound. So if we look at this expression, P empty is kind of guaranteed to be at least a constant if epsilon is at least half. You can show that quite easily just by looking at this bound. So this expression looks something like e power minus some constant times m epsilon squared, and this is basically the probability of error, essentially, because the error is only made if the estimate goes far away from the true value. So finally, if we plug in the value for m as log n by epsilon squared, so essentially here we have some constant times m epsilon squared. So if we plug in m equals log n by epsilon squared, the epsilon squared cancels, and we essentially get e raised to the power of some constant times log n, and that basically becomes 1 by n power some constant. So essentially this error probability just becomes 1 by some polynomial in n when we do this. And that is something that's very small, essentially. That's the key idea here. So essentially what we've shown is that when we set m to be equal to order of log n by epsilon squared, then our error probability is 1 by polynomial in n. And so our algorithm is going to succeed with a very high probability that's close to 1. So finally, what we've essentially shown here is that if we have the ability to efficiently solve our emptiness problem, then with just an order log n factor overhead in space and time, log n by epsilon squared overhead, we can efficiently solve this decision problem associated with it as well. So finally, we'll put everything together, everything we've seen so far together, and we'll see what this algorithm actually translates to in terms of space and time guarantees for this half-plane range counting problem that we're looking at. So we saw in the last video that the exact depth calculation problem or range counting problem is hard when our ranges are half planes. And in particular, if we want to solve the range counting problem exactly in polylog time, then we need order n cube space. And on the flip side, if we have linear space, then the best we can do is order n to the power 2 by 3 query time for range counting. And this was the reason we started looking at the approximate range counting problem and depth estimation problem in the first place. So let's see if the algorithm we've come up with is actually an improvement over this lower bound for exact depth calculation. So once again, the algorithm we described uses, as I said, uses an algorithm for emptiness as a black box subroutine. And for half planes in particular, as I mentioned in the last video, this problem of solving emptiness for half planes was solved by Dawkins and Kirkpatrick in 1985, and they came up with a linear space data structure that can answer emptiness queries in order log n time. So if we use this data structure and algorithm as a black box in our estimation problem, what do we get? So first of all, let's look at the decision version. So every emptiness data structure, as mentioned just above, takes linear space, and our algorithm generates m different data structures, where m we calculated to be order log n by epsilon squared. So the total amount of space that we need is just n times log n by epsilon squared. And in the same way, in terms of time to answer the queries, we need log n time to answer a single emptiness queries. And for any input range, our algorithm is going to make m different emptiness queries, where m is again log n by epsilon squared, and this kind of contributes to all the runtime. So the query time is something like log n times log n by epsilon squared, which is basically order log square n, as we see over here. So these are the guarantees for the decision problem. And finally, when we go to the full estimation problem itself, what we saw is that to solve the estimation problem, we can do that by constructing this exponential grid of thresholds of size order log n by epsilon. And we have to basically build log n by epsilon different decision problem data structures to answer the estimation queries. So the space complexity is basically increased by another factor of log n by epsilon. So from epsilon square n log n, we multiply that by another log n by epsilon to get epsilon to the power minus 3 times n log square n. That's our space. And in terms of query time, what we saw is that we had this nice little trick. Instead of actually running all of these log n by epsilon different decision queries, we can do a binary search instead. and only run log n by epsilon different decision queries. So basically, the query time goes up by a factor of log n by epsilon, essentially, compared to the query time of the decision problem. So overall, if we look at these final expressions here, if we fix our value of epsilon, the space is like n times log square n, and that is very close to linear. It's essentially just n times logarithmic polylog factor above linear. And the query time is basically something like log square n times log n. So this is some polylogarithmic query time. So finally, to conclude, what we've managed is that we've constructed an algorithm that achieves near linear space and polylogarithmic query time to solve this depth estimation problem for any fixed epsilon. That's a huge improvement over the cubic space that we needed for this same kind of guarantee if we want to do exact depth calculation. So we really do have a tangible improvement by doing this by doing whatever we've done, going to emptiness and then using this randomness. So that concludes this talk. So here are some of the papers and references that were used in making this talk, and in particular, Sari and Arpalet's book on geometric approximation algorithms has a really nice section on topics related to depth estimation. And the book also talks about this algorithm and several other applications of depth estimation. And the lecture slides that we used for this video are also linked in the video description. So yeah, that's it everyone. We'll wrap up the video here. Thanks for watching.